Picture the edge of the world. A place where the air itself seems to hold its breath, where the only sound is the whisper of wind carving invisible patterns across frozen eternity. Greenland stretches beneath the pale Arctic sun like a sleeping giant, its skin of ice gleaming in shades of silver and blue that no photograph can truly capture. From above, it appears lifeless, a continent locked in stasis, untouched and untouchable. But silence, as any traveler knows, is never truly empty. Beneath that white expanse lies something far older than the ice itself. Layer upon frozen layer, millennium stacked upon millennium, the glaciers hold their secrets close. And now, for the first time in human memory, they are beginning to speak. A melt has started, not with violence, but with a quiet persistence. Drip by drip, stream by stream, the ancient ice surrenders to warmth. What emerges is not merely rock and soil, but fragments of a story the world has forgotten. Coastlines that haven't seen sunlight in 100,000 years. Riverbeds carved when mammoths still walked the earth. And perhaps, just perhaps, traces of something even more impossible. As the camera drifts across crevasses deep enough to swallow cathedrals, across fields of blue ice that glow like stained glass, one question lingers in the thin, cold air. What else has the ice been hiding? And more troubling still, what will we remember when it finally lets go? Scientists call it a time machine. Greenland's ice sheet, nearly 2 miles thick at its deepest point, is one of the most complete climate archives on Earth. Each winter's snowfall compresses into a thin band of ice, trapping tiny bubbles of ancient atmosphere. Drill down through these layers, and you're traveling backward through time, past the Industrial Revolution, past the rise and fall of Rome, past the birth of agriculture itself, into ages when the planet wore a different face entirely. Researchers in insulated labs examine cores pulled from the depths, reading them like tree rings. They can tell you the temperature of the air 10,000 years ago. They can measure the concentration of carbon dioxide when the pyramids were being built. They can even detect volcanic eruptions from the opposite side of the globe, their ash frozen into the ice like punctuation marks in an unwritten history. But among these meticulous records are whispers that don't quite fit. Warm periods appearing where there should be only cold. Pollen from temperate plants found at depths suggesting impossible dates. Chemical signatures that hint at liquid water flowing on the surface when, according to every model, Greenland should have been locked solid. These anomalies trouble the comfortable narrative. They suggest that the ice has not always ruled this land, that there have been intermissions in the frozen performance, warm interludes when life could flourish. And if life could flourish, then perhaps. But no, that speculation must wait. For now, the ice cores sit in their frozen vaults, testimonies to a planet that has breathed in and out across geological epochs, expanding and contracting its frozen lungs in rhythms we are only beginning to understand. Each core is a book, each anomaly a footnote that demands explanation. The ice remembers everything. The question is whether we're ready to hear what it has to say. Beneath the surface, invisible to the naked eye, another Greenland waits. Modern sonar technology has pierced the ice, sending radar waves down through the frozen depths to map the hidden bedrock below. What those waves revealed sent ripples through the scientific community, not the barren, scoured landscape they expected, but something far more complex. Valleys carved with the patient precision of ancient rivers. Coastlines marking seas that dried up before human civilization began. Mountain ranges that once stood proud against a different sky. The topography beneath Greenland's ice tells a story of water and warmth. These are not the random scratches of advancing glaciers, but the careful architecture of erosion over vast stretches of time, rivers meandering toward forgotten oceans, deltas spreading their fingers into bays that no living thing remembers. Some of these features date back millions of years, to epochs when Greenland truly lived up to its name. Others are more recent, geologically speaking, formed during brief interglacial periods when the ice retreated and the land breathed free. But even recent in this context means tens of thousands of years, epochs when Homo sapiens was just beginning its long journey out of Africa. Could humans have reached these northern shores during one of those warmer interludes? The mainstream answer is no, too early, too remote, too difficult. Yet the valleys beneath the ice speak of a land that was once habitable, even welcoming. Rivers need rainfall. Coastlines imply moderate temperatures. Valleys suggest shelter. If the land was green, could it have been empty? The question hangs in the air, like mist over those invisible, frozen valleys. The sonar images show us the stage, but the actors, if there ever were any, remain hidden beneath 2 miles of accumulated time, waiting for the melt to finally bring them into the light. The accepted history is far simpler, far more recent, and infinitely more certain. According to the archaeological consensus, human beings first set foot on Greenland roughly 4,500 years ago. These were the Sakak people, part of the broader Paleo-Eskimo migration that had island-hopped across the Canadian Arctic. They came not as explorers or adventurers, but as survivors, following the animals they hunted, adapting to one of the harshest environments on Earth, with nothing but stone tools, bone needles, and an intimate knowledge of ice. Their traces are few, but telling. Hearths where they burned bone and driftwood for warmth. Harpoon points carved from walrus ivory. The remains of small, ingeniously constructed dwellings half buried in the permafrost. They lived along the coasts, harvesting seals and fish, enduring the endless winter darkness with a resilience that borders on the miraculous. After the Sakak came the Dorsic people, and later the Thule ancestors of modern Inuit populations. Each culture left its mark: more sophisticated tools, different hunting techniques, subtle shifts in dwelling construction. Archaeologists have pieced together these fragments into a timeline that spans millennia, a story of human persistence against impossible odds. But it is also a story with significant gaps. The permafrost preserves what it touches, yes, but it also conceals. Large portions of Greenland's habitable coastline remain buried beneath ice or have been scoured clean by glacial advance and retreat. What existed before the Sakak during the warmer periods, hinted at by climate data, remains largely invisible to conventional archaeology. The official story is one of late arrival and harsh survival. It's a narrative backed by evidence, confirmed by carbon dating, supported by decades of careful excavation. And yet, as the ice continues its slow retreat, revealing landscapes that haven't been exposed in thousands of years, one can't help but wonder, is this the complete story? Or merely the most recent chapter in a much longer, stranger book? The ice is a storyteller, but it speaks in a language older than words. As Greenland's glaciers retreat at accelerating rates, some losing billions of tons of mass each year, they leave behind more than just exposed rock. The meltwater carries with it the compressed memories of ancient ecosystems, pollen grains from flowers that bloomed millennia ago, fragments of leaves from trees that once formed vast forests, bones of animals that grazed on long-vanished grasslands. Scientists collecting samples from the meltwater streams have been astonished by the diversity of what emerges. Spruce pollen, birch bark, seeds from plants typically found hundreds of miles farther south. The biological evidence paints a picture radically different from the frozen wasteland we associate with Greenland today, a landscape of boreal forests, flowing rivers, and meadows alive with vegetation. Some of this organic material dates back to the most recent interglacial period, roughly 120,000 years ago. But other samples are younger, much younger, suggesting that Greenland experienced periods of relative warmth, even within the time frame of modern human existence. Periods when Greenland might have actually been green. This raises uncomfortable questions for the traditional timeline. If Greenland was partially ice-free and covered with vegetation as recently as several thousand years ago. Why do we have no record of human habitation during those periods? Did the first humans simply miss this opportunity, arriving only after the cold had returned? Or did they arrive, live, and leave traces that have since been swallowed by the returning ice? The Norse settlers of the medieval period certainly found a more temperate Greenland than exists today. Their sagas describe lush valleys where they raised cattle and sheep, where crops grew during the brief but intense Arctic summer. For several centuries, they thrived until the climate shifted, the ice advanced, and they vanished into history's gaps. Perhaps they were not the first to experience this cycle of warmth and cold, arrival and disappearance. Perhaps the ice has witnessed this pattern before, many times before, rising and falling like breath, each exhalation erasing what came during the inhalation. The meltwater carries these possibilities downstream, mixing ancient pollen with modern water, past with present, certainty with mystery. In the year 982, a Viking named Eric the Red arrived at Greenland's southwestern coast and made a decision that would echo through history. He named it Greenland. Whether this was clever marketing or accurate description remains debated, but the Norse who followed him found a landscape far more hospitable than the name Greenland suggests today. They established two main settlements, the eastern and western settlements, ironically, both on the western coast. At their peak, these communities supported perhaps 5,000 people, with farms, churches, and trade connections stretching back to Iceland and Norway. The archaeological evidence paints a picture of surprising prosperity. Stone ruins of farmsteads still stand, their walls enclosing what were once fields for hay and pasture for livestock. The Norse kept cattle, sheep, and goats. They hunted caribou and seals. They exported walrus ivory, polar bear pelts, and narwhal tusks to European markets, hungry for exotic goods. But most remarkably, the climate records from this period, the medieval warm period, roughly 950 to 1250 CE, confirm that Greenland was indeed warmer. Sea ice was less extensive, allowing easier navigation. Growing seasons were longer. The Norse weren't delusional or exceptionally hardy. They were living during a climatic anomaly, a brief window of relative warmth. Then, gradually, that window closed. By the 1400s, the settlements were abandoned. The last written record dates to 1408, a wedding certificate. After that, silence. When European ships returned centuries later, they found only ruins and mystery. What happened to the Norse Greenlanders? The mainstream explanation points to the Little Ice Age, a cooling period that made farming impossible and choked the sea routes with ice, cutting the settlements off from resupply. Faced with starvation and isolation, the survivors either died or returned to Iceland. It's a logical, evidence-based explanation. But there are oddities that trouble this neat conclusion. Some ruins show signs of sudden abandonment, with possessions left behind. Others suggest a gradual decline, but no clear exodus. And the Inuit, who are expanding into the area at the same time, have oral traditions that hint at conflict, and Norse settlements still occupied when Thule hunters arrived. What is certain is that the Norse experience demonstrates how profoundly Greenland's climate can shift within a human lifespan, how a land can give and then take away, how warmth can be a temporary guest rather than a permanent resident. As modern glaciers retreat once more, revealing Norse ruins that have been ice-covered for centuries, one wonders, is this pattern of warming and cooling a recent phenomenon? Or has Greenland been oscillating between green and white for far longer than we realize, each cycle burying the evidence of the previous one beneath fresh layers of ice? The Vikings arrived during a warm period, thrived, and vanished when the cold returned. But perhaps they were not the first to follow this script. Perhaps the play has been performed many times with different actors on the same frozen stage. Deep beneath Greenland's ice, in cores extracted from 2 miles down, Scientists have found something that shouldn't exist: life. Not living organisms, but their genetic ghosts, fragments of DNA preserved in frozen sediment for over 2 million years. These are the oldest authenticated genetic sequences ever recovered, pushing back the boundaries of what we thought possible for molecular preservation. The species list reads like a speculative ecosystem: spruce trees, yew, butterflies, beetles, mastodons, reindeer, and even ancient relatives of modern rabbits and geese. But most intriguing are the botanical samples' DNA from flowering plants that today exist only in much warmer climates, thousands of miles to the south. This genetic archive confirms what geologists had long suspected: that Greenland, in the distant past, supported a boreal forest ecosystem similar to the taiga of modern Alaska or Siberia. Where today there is only ice and rock, there once stood forests thick enough to support large mammals, diverse enough to sustain insect populations, warm enough for flowers to bloom and set seed. 2 million years is an almost incomprehensible span of time. It predates the genus Homo by a comfortable margin. It's a window into a world before ice ages became the dominant rhythm of Earth's climate, when the planet's temperature fluctuated but generally remained warmer than today. Yet here is the troubling implication: if DNA can survive for 2 million years in Greenland's ice, then theoretically, genetic material from more recent epochs should also be preserved. Material from the last interglacial period, 120,000 years ago. Material from brief warm intervals during the current ice age. Material from any life plant, animal, or otherwise that existed during those temperate interludes. The question becomes, what else might be hiding in those cores that hasn't been sequenced yet? What organic traces from more recent epochs might be waiting for the right lab technique, the right question, the right search? The permafrost is a library. We've barely read the introduction. And as the ice melts and the oldest frozen archives begin to thaw, some scientists worry we might lose invaluable pages before we even know they exist. Genetic histories erased by the very warmth that once created them, stories told only once as the ice weeps them into oblivion. There is water in Greenland that has never seen the sun. Beneath the crushing weight of ice, in darkness absolute and cold that should freeze everything solid, rivers flow. Not metaphorical rivers, but actual liquid water channels, sometimes miles wide, flowing through caverns carved from the ice itself or along the bedrock below, moving at speeds that would surprise anyone expecting glacial stillness. Radar mapping and seismic studies have revealed a vast network of these subglacial waterways. They form and reform, carving new paths through the ice, pooling into hidden lakes the size of small seas, then draining catastrophically in floods that lubricate the glacier's slow march toward the ocean. The physics are counterintuitive. How does water remain liquid under such conditions? The answer lies in pressure and geothermal heat. The immense weight of overlying ice lowers water's freezing point, while heat from Earth's interior conducted through the bedrock provides just enough warmth to maintain liquid flow. In some areas, friction from the glacier's movement generates additional heat, creating a self-sustaining system of melting and flow. But in certain regions, the water is warmer than it should be, significantly warmer. Scientists have detected thermal anomalies beneath the ice spots where the bedrock radiates heat beyond what simple geothermal gradients can explain. Some of these are attributed to volcanic activity. Greenland sits atop geological structures that were once far more active. Ancient magma chambers, long since cooled, still release the residual warmth into the overlying rock. Others are harder to explain. Magnetic surveys reveal unusual patterns in the bedrock, variations in mineral content that suggest complex geological histories. In some areas, the rock beneath the ice is surprisingly young, geologically speaking, hinting at volcanic or hydrothermal activity within the last few 100,000 years. These hidden rivers have practical implications. They destabilize glaciers, causing massive ice sheets to slide faster toward the sea. They complicate predictions about sea level rise. But they also raise intriguing questions about Greenland's past. If volcanic systems kept parts of the bedrock warm, even during the depths of ice ages, could there have been ice-free oasis pockets of liquid water and relative warmth surrounded by frozen wasteland? Could life have persisted in these hidden refugia, waiting for the ice to retreat? The subglacial rivers are Greenland's circulatory system, carrying heat and dissolved minerals through channels no human eye has ever seen. They are evidence that even in the heart of the frozen world, nothing is truly still. Beneath the white silence, the water whispers, carving stories in the dark. The ice has not always been there. This is perhaps the most disorienting realization for those who think of Greenland as eternally frozen. The ice sheet is a relatively recent phenomenon in geological terms, and it has come and gone multiple times throughout Earth's history. Approximately 2.7 million years ago, glaciers began forming on Greenland as global temperatures dropped and ice ages became cyclical. But the ice sheet as we know it today, that massive dome covering 80% of the island, is younger still, building to its current thickness only within the last million years. And even during that period, it has disappeared completely. Sediment cores drilled from the ocean floor around Greenland tell a revealing story. They contain layers of rock debris that could only have been deposited by icebergs, proof of glaciation alternating with layers of marine mud devoid of ice-rafted material. These mud layers indicate periods when Greenland's coasts were ice-free, when rivers flowed unobstructed to the sea, when glaciers survived only in mountain valleys, if they survived at all. The most recent complete melting occurred during the Eemian interglacial period, roughly 130,000 to 115,000 years ago. During this time, global temperatures were 1 to 2 degrees Celsius warmer than today. This is not theoretical. The evidence is written in coral reefs that grew at higher elevations, in beach deposits now found inland, in the chemical signatures of ancient seawater. But here is where the story becomes troubling for the present day, that Eemian warming was caused by natural orbital variations, shifts in Earth's position relative to the Sun that are well understood. Today's warming is happening faster, driven by human-altered atmospheric chemistry. If Greenland's ice could vanish during a warming period less intense than what we're creating now, what does that imply for the future? More immediately, what does it imply for the past? If Greenland was ice-free during the Eemian well, within the time frame of Homo sapiens' existence as a species, could early humans have reached its shores? But absence of evidence is not evidence of absence, particularly when much of the potential evidence would be buried under the returned ice or drowned beneath risen seas. Each time it returns, it buries the evidence anew. We live in an interglacial period, now one of the warm interludes between ice ages. The ice is retreating. The cycle continues. And as it does, we might finally glimpse what was written during the last warm chapter, before the ice came back and covered the pages once more. 120,000 years ago, Greenland breathed differently. The Eemian interglacial was a time of warmth that today climate scientists study with a mix of fascination and apprehension. It represents Earth's most recent natural experiment in a warmer world, a preview, perhaps of what we're creating now, but one that played out according to the planet's own rhythms rather than human intervention. During this period, much of Greenland's ice sheet melted away, leaving behind a landscape that would be unrecognizable to modern observers. Forests of pine and spruce spread across the southern regions. Tundra vegetation pushed far north, covering areas that today are locked beneath glaciers. Rivers carved deep valleys, flowing year-round rather than freezing solid in winter. Lakes dotted the interior, supporting ecosystems of fish, birds, and insects. We know this from the biological evidence trapped in ice cores and sediment layers pollen, plant fragments, insect chitin, all preserved in the muck of ancient lake beds that now lie buried again beneath ice. DNA analysis confirms that species assemblages existed, which have no modern analog, unique combinations of flora and fauna adapted to Greenland's particular blend of warmth and Arctic daylight cycles. But the Eemian holds an even more tantalizing secret. Evidence suggests that not all of Greenland's ice melted. Computer models and geological data indicate that while the southern and coastal ice disappeared, a smaller ice sheet persisted in the island's interior highlands, a refugium of cold in a warming world. This partial melting raises profound questions about sea level. During the Eemian, oceans rose 6 to 9 meters higher than today, drowning coastlines worldwide. Coral reefs that formed then are now high and dry, fossil monuments to seas that once lapped against different shores. Some of that water came from Greenland, but not all Antarctica contributed as well, perhaps significantly. For any coastline civilization of that era, the rising seas would have been catastrophic. Of course, there were no civilizations not as we understand them. Homo sapiens existed, but had not yet begun the population explosion that would carry them to every continent. The world's human population likely numbered in the tens of thousands, scattered across Africa, and perhaps just beginning to venture into the Middle East. And yet, the Eemian lasted 15,000 years. That's longer than the entire span of recorded human history. Long enough for languages to evolve, for technologies to develop, for cultures to rise and fall. If humans had reached Greenland during that epoch, a possibility entirely unsupported by current evidence, but not physically impossible, any trace of them would now be either deep underwater, sea levels rose after the ice returned, or buried under the renewed glaciation. The forgotten green epoch is forgotten not by choice, but by geology. Time has a way of covering its tracks, and Greenland's ice is time's favorite accomplice. The Eemian world was green, alive, and vibrant. Then the cold returned, and the manuscript was erased, leaving only faint chemical traces of what once grew and flew and perhaps walked across those vanished forests. As modern ice retreats once more, we are seeing the same landscapes exposed that last breathed free air 120,000 years ago. The cycle completes, the land emerges, and we are left to wonder, what else will emerge with it? In 1513, a Turkish admiral named Piri Reis compiled a world map that would trouble historians for centuries. The map itself is a work of scholarly compilation, drawing on dozens of source maps, including, according to Piri Reis's own notes, charts captured from Christopher Columbus. It shows the coasts of Europe, Africa, and the recently discovered Americas with remarkable accuracy for its time. But it has one particular detail that has sparked endless debate. The southern edge of the map appears to show Antarctica's coastline, and it shows it without ice. More relevant to our story is another cartographic anomaly, one that appears on several Renaissance-era maps. Greenland depicted with geographic details that shouldn't have been known until satellite radar mapping in the 20th century. The Orontius Phineas map of 1531 shows Antarctica, yes, but it also depicts Greenland with an interior free of ice, showing what appear to be rivers, mountain ranges, and a landscape contour that matches eerily the topography that modern sonar has revealed beneath the ice sheet. The Zeno map of 1380 shows Greenland's coastline with fjords and inlets positioned with surprising accuracy, despite being drawn centuries before proper surveys. The conventional explanation is straightforward. The cartographers were speculating, filling in gaps with imagination, or copying errors from earlier maps. After all, the idea that anyone could have mapped ice-free Greenland implies an accuracy of record-keeping and knowledge transfer across vast time spans that seems to defy everything we know about pre-modern societies. And yet, the defenders of these maps' anomalous accuracy point out specific correspondences. The shape of Greenland's bedrock coast, hidden beneath miles of ice until the 1950s, matches details on maps drawn 400 years earlier. The position of inland features mountains, valleys aligns with radar data that wouldn't exist for centuries. Could the Renaissance cartographers have been working from much older source maps? Maps drawn during warmer periods when parts of Greenland were ice-free and navigable? The theory strains credibility, requiring not just ancient exploration, but also the preservation and transmission of accurate geographic information across millennia. Most historians reject the idea entirely. Coincidence, they argue, combined with selective interpretation and confirmation bias. When you look hard enough for correlations, you'll find them even in random data. But the maps remain tantalizing and strange. Piri Reis himself claimed to be working from ancient sources, maps from the time of Alexander the Great and earlier. Whether this was truth or a cartographer's mystique is impossible to know. What's certain is that during warmer periods, the medieval warm period, the Romang warm period, and especially the Eemian interglacial Greenland would have been more accessible, its coasts clearer, its interior more exposed. If any civilization during those epochs had reached these northern waters, they could theoretically have mapped what they saw. The problem is the preservation gap. How would such maps survive the cold centuries in between? How would they be copied and transmitted across cultures that rose and fell? The logistics of such knowledge transfer are staggering. Perhaps these maps are simply what mainstream academia says, interesting artifacts of Renaissance curiosity, filled with speculation and artistic license. Or perhaps they are faint traces of something older, echoes of an age when Greenland's secrets were not quite so deeply buried, when someone, somewhere, saw the land without its frozen mask and carefully drew what they saw. The maps pose a question rather than providing an answer. In an age when satellite technology can see through ice and computers can model ancient climates, we have the tools to check the mapmakers' work. And in some cases, impossibly, their work checks out. Beneath the ice of northern Greenland, something massive lurks in the bedrock. Magnetic surveys conducted over the past decades have revealed an enormous anomaly stretching hundreds of kilometers across the subglacial landscape. The magnetic field strength in this region deviates significantly from surrounding areas, suggesting a concentration of iron-rich minerals, or perhaps something even more unusual buried in the ancient rock. The leading theory is impact a massive asteroid or meteorite strike sometime in the deep past. When extraterrestrial objects slam into Earth, they often contain high concentrations of nickel iron, and the impact itself can magnetize surrounding rock. Several confirmed impact structures show similar magnetic signatures. In 2018, scientists announced the discovery of a 31-kilometer-wide crater buried beneath the Hiawatha Glacier in northwest Greenland, the first impact crater ever found under ice. Magnetic data had pointed the way. Dating of the impact remains uncertain, but estimates range from as recent as 13,000 years ago to over 3 million years, a frustratingly wide window. If the younger date is correct, the timing becomes provocative. 13,000 years ago corresponds to the Younger Dryas, a mysterious period when global temperatures plunged suddenly, interrupting the warming trend that was ending the last ice age. Ice cores from Greenland show the shift happened within decades, perhaps within years. Climate change on a civilizational timescale. Could an impact have triggered this cold snap? The hypothesis is controversial, but not impossible. A large asteroid striking Greenland's ice sheet could have thrown massive amounts of water vapor and ice crystals into the atmosphere, creating a temporary nuclear winter effect. It could have disrupted ocean currents, altered atmospheric circulation, and generally shocked Earth's climate system. But the magnetic anomaly extends far beyond the Hiawatha crater. There may be other impacts, older and deeper, their craters eroded or completely buried. Or the anomaly might reflect ancient volcanic structures, Intrusions of magma-rich rock pushed up from the mantle millions of years ago when Greenland was geologically active. What makes this odd fact particularly intriguing is what it suggests about the landscape beneath the ice. These magnetic signatures are windows into deep time, markers of events that shaped the land long before ice covered it. They remind us that Greenland as story doesn't begin with the glaciation. It begins billions of years ago with the formation of continental crust, continues through volcanic epochs and asteroid bombardments, and only in its most recent chapter involves ice at all. The magnetic whisper from beneath the ice is a reminder that we're skating on the surface of much deeper mysteries. Each anomaly detected, each unusual reading in the magnetometer data is a hint that the frozen library contains volumes we haven't yet learned to read, stories written in rock and metal rather than ice and snow, tales of cosmic violence and tectonic drama that make even the comings and goings of ice sheets seem like footnotes. Somewhere under northern Greenland, the magnetic field bends and swirls around ancient secrets. And as the ice thins and our instruments improve, we may finally learn what scars the land still carries from ages before ice ever mattered. The Inuit have always known about the ice's power. Their oral traditions, passed down through generations in the long darkness of Arctic winters, speak of a time before the cold, when the land was warm and animals now vanished roamed freely. They tell of Sedna, the goddess of the sea, and her terrible power over ice and storm. They remember when the white breath came down from the sky and covered the earth, transforming the world in a single generation. To Western ears, trained to separate myth from history, these stories sound like metaphor or spiritual allegory. But anthropologists studying indigenous oral traditions have found that they often contain kernels of genuine historical memory, events preserved with surprising accuracy across vast spans of time. The Inuit speak of the land that slept under white breath, a phrase hauntingly evocative of glaciation. Some stories describe ancestors fleeing southward as the cold advanced, ice appearing where green valleys had been, the sea freezing solid, animals disappearing. Other tales speak of a time even earlier, when fire came from the sky and the ice covered everything to protect the world from burning. Could these be memories of real climate shifts, encoded in narrative form? The Younger Dryas cold snap occurred about 13,000 years ago, well within the span that oral traditions can preserve, particularly in cultures with strong mnemonic practices. Indigenous Australian stories have been shown to accurately describe coastline features that were drowned by rising seas over 10,000 years ago. If the Inuit stories preserve genuine memory, they would represent human testimony to one of the most dramatic climate events in recent geological history, the end of the Ice Age. From a human perspective, living through such transitions, the changes would have seemed divinely ordained, the work of gods angry or protective. Other circumpolar cultures share similar themes. Norse mythology speaks of Fimbul winter, the great winter that precedes Ragnarok, when snow falls from all directions and the sun loses its warmth. Indigenous Siberian peoples have stories of ancient cold descending like judgment. Even far to the south, flood myths dominate the mythologies of dozens of cultures, perhaps memory of the seas that rose when the great ice sheets finally melted. There's a peculiar overlap between myth and geology in these northern stories. The gods of ice and snow aren't just feared. They're remembered as having specific historical moments of intervention. The world was one way, then the gods acted, and it became another way. This is the narrative structure of climate change, of environmental catastrophe, viewed through the lens of pre-scientific understanding. Modern science can now map Greenland's ice advances and retreats with remarkable precision, reading the story in oxygen isotopes and ice core stratigraphy. But perhaps the Inuit elders, sitting in their winter shelters, were reading the same story in their own way, preserving in the amber of oral tradition what the ice cores preserve in frozen bubbles. Testimony that the world has changed before, dramatically and rapidly, and that those who witnessed it never forgot. As Greenland's ice retreats once more in our own era, one wonders what stories future generations will tell. What myths will encode our experience of warming seas and melting glaciers? Will they remember us as the generation that witnessed the ice's departure, or as the generation that caused it? The old stories suggest the ice will return eventually, that this is a cycle, not an ending. The geological record agrees. But the human timescale and the glacial timescale operate on different rhythms. For us, for our civilizations, what happens to Greenland's ice is not mythical but immediate, not cyclical but catastrophic. Perhaps that's why the old myths resonate so powerfully. They remind us that humans have watched the ice advance and retreat before. They survived, they remembered, they told stories. And now those stories, like the ice itself, are melting back into relevance. There is a rhythm to the planet's breathing. Earth oscillates between ice ages and interglacial periods with a regularity that scientists have only recently begun to understand. The pattern is driven by subtle wobbles in the planet's orbit and axial tilt-Milankovitch cycles, named after the Serbian mathematician who first calculated them in the 1920s. Every 41,000 years, every 100,000 years, every 23,000 years, the geometry of Earth's orbit shifts slightly, changing the distribution of solar energy across latitudes and seasons. These tiny astronomical variations are enough to tip the planet between frozen and temperate states. When northern summers receive less solar energy, snow accumulates year after year, building into glaciers. Ice reflects more sunlight than Earth or ocean, creating a positive feedback loop. More ice means more reflection, means more cooling, means more ice. Eventually, vast ice sheets grind southward from the poles, covering continents. Then the orbital geometry shifts again. Northern summers brighten, the ice begins to melt, and the cycle reverses. The planet warms, seas rise, life migrates northward. For a brief period, geologically brief, though it may last 10 or 15,000 years from a human perspective, the world is temperate, ice confined to polar regions and high mountains. We live in one of these interglacial periods now, though its behavior is being dramatically altered by human influence. But the underlying pattern remains. The ice will eventually return. Not tomorrow, not in 1,000 years, but eventually. Earth's natural state for the past 3 million years has been glacial, with warm periods like ours being temporary exceptions. This is the pulse that Greenland knows intimately. With each glacial cycle, the ice sheet grows and shrinks, advances and retreats, covering and uncovering the land. And with each cycle, any evidence of what existed during the previous warm period is scoured away or buried deep. Now consider the implications for human history. Homo sapiens has existed for roughly 300,000 years, long enough to experience multiple glacial-interglacial transitions. Our species lived through the depths of the last ice age, when ice sheets covered much of North America, Europe, and Asia. We witnessed the dramatic warming and ice retreat that began about 20,000 years ago. We adapted to coastlines drowning as meltwater raised sea levels by over 120 meters. And if we existed through those transitions, might previous human species, Neanderthals, Denisovans, Homo erectus, have experienced earlier ones? Might they have settled in regions that were temporarily habitable, only to be forced out when the ice returned? The pulse of climate is also a pulse of opportunity and catastrophe. When the ice retreats, new lands open for settlement. When it advances, populations must migrate or perish. When sea levels rise, coastal settlements drown. When they fall, new coastal plains emerge. This rhythm might explain some of the mysteries and human prehistory gaps in the archaeological record: sudden population movements, the disappearance of entire cultures. If significant human activity occurred in regions that were later glaciated, we would find no trace of it. The ice would have ground the evidence to dust. Greenland is a particularly tantalizing example because it sits at the margin, sometimes covered, sometimes exposed, sometimes partially habitable. During each warm period, it offers opportunity. During each cold return, it becomes forbidden territory, and anything left behind is sealed away. The planet's pulse continues. At present, the beat is quickening in an unnatural way, driven not by orbital mechanics, but by atmospheric chemistry, by the accumulated breath of machines. We are adding a new verse to an ancient song, and Greenland's ice is responding, melting faster than at any point in recorded history. As it melts, we're witnessing in decades what usually takes millennia: the exposure of landscapes, the release of locked-away evidence, the potential revelation of secrets that have lain frozen for thousands of years. The pulse of climate is also the pulse of memory. Each warm period, the planet remembers. Each cold return, it forgets. And we, living through this particular transition, are both witnesses and participants, watching ancient rhythms and creating new ones, all at once. The bedrock of Greenland holds shapes that trouble the imagination. When researchers first processed high-resolution radar data from beneath the ice, mapping the contours of the hidden landscape, they expected valleys, mountains, the typical architecture of erosion and tectonic uplift. What they found included all of that, but also features that seemed oddly regular, geometrically precise in ways that natural erosion rarely produces. There are terraces along subglacial valleys, step-like formations, where one would expect smooth slopes. There are ridges that run parallel to each other for kilometers, too regular to be simply the result of random glacial scouring. There are circular formations, some kilometers across, their geometry disturbingly perfect. The scientific explanation is straightforward. These are natural geological features, perhaps created by specific patterns of glacial flow, or by ancient volcanic activity, or by particular types of erosion acting on layered sedimentary rock. Geology can produce remarkably regular patterns. Columnar basalt, for instance, forms nearly perfect hexagons, and certain erosion patterns create structures that look artificial but are entirely natural. And yet, the speculative mind wanders. If Greenland was ice-free during previous interglacial periods, and if humans or precursor species reached those shores, might they have built structures? And if they did, would anything remain after 100,000 years beneath grinding ice? The honest answer is, almost certainly not. Ice is patient but thorough. A glacier doesn't simply sit atop the land. It flows, grinds, crushes, and excavates. Anything built on the surface would be pulverized within centuries. Stone structures might last longer, but even granite eventually succumbs to the relentless pressure of ice kilometers thick. However, and this is where speculation finds its foothold, bedrock formations can persist. If structures were somehow carved into or built in harmony with the underlying stone, if they were protected in certain topographic positions, if ice flow patterns happened to preserve rather than destroy them, then perhaps. But this is speculation piled upon speculation, a tower of F's with no foundation in evidence. What the subglacial mapping really shows us is how little we've actually seen of Greenland. The island we know, the one visible to satellites and visitors, is merely the surface of the ice. The actual land, the rock and soil that constitutes Greenland itself, has been hidden for millennia. We're only now beginning to map it comprehensively, and what we're finding is more complex than anticipated. Some of these formations deserve closer study. If and when the ice retreats enough to expose them, or if drilling projects can extract more detailed core samples, we'll have better answers. Until then, they remain intriguing shapes in radar data, patterns that might mean everything or nothing. The stone beneath the glacier is patient. It has been there for millions of years and will remain long after the current ice age ends. Whether it holds any secrets beyond geological ones is a question that only time, or the ice's continued retreat, will answer. For now, we're left with shadows on sonar screens, geometries that catch the eye and spark the imagination, shapes beneath the white silence that may be entirely natural or may be waiting to tell a story we haven't yet learned to hear. In 1959, at the height of the Cold War, the United States military embarked on one of the most audacious engineering projects ever attempted in the Arctic. Camp Century, billed publicly as a research facility for ice core studies and Arctic survival techniques, was actually a cover for something far more ambitious and more troubling: Project Iceworm, a plan to install a network of mobile nuclear missiles beneath the Greenland ice sheet. The facility itself was powered by a portable nuclear reactor and consisted of tunnels carved directly into the ice, creating an underground city where 200 personnel could live and work in sub-zero conditions. The military project was eventually abandoned. The ice proved less stable than anticipated, the tunnels constantly deforming and requiring maintenance. By 1967, Camp Century was closed, its nuclear reactor removed, its equipment mostly left behind to be slowly crushed by the ice's inexorable movement. But during its brief existence, Camp Century scientists drilled deep into the ice, extracting cores that would revolutionize climate science. They reached bedrock at a depth of 1,390 meters, pulling up ice that was over 100,000 years old, the first successful deep ice core from Greenland. And at the very bottom, in the last meters of core extracted from the interface between ice and bedrock, they found something unexpected: sediment containing plant material. At the time, this discovery didn't generate much attention. The cores were stored at military facilities, and the focus was on the atmospheric data trapped in ice bubbles, not on the dirt from the bottom. For decades, these samples sat in frozen storage, a footnote to the larger Cold War narrative. Then, in 2019, a researcher at the University of Copenhagen rediscovered those forgotten sediment samples. Modern analysis revealed their true significance. They contained organic material leaves, twigs, seeds from plants that could only have grown in an ice-free environment. Radiocarbon and other dating techniques suggested the material was roughly 400,000 to 1 million years old, though such extreme ages pushed the limits of dating precision. The implication was clear. At some point in the relatively recent geological past, the bedrock beneath Camp Century had been exposed to air and sunlight. Plants had grown there. Forests had stood where now there was only ice. This was direct physical evidence that Greenland's ice sheet is more fragile than previously assumed, that it has disappeared entirely during past warm periods, not just thinned, but vanished, allowing ecosystems to establish on the exposed land before the ice returned. For climate scientists studying contemporary ice melt, the Camp Century samples are both reassuring and deeply troubling. Reassuring because they confirm that natural climate variability can indeed melt the ice sheet. It's not a permanent, indestructible feature. Troubling because if it melted during previous warm periods that were less intense than the warming we're recreating now, then its complete disappearance in coming centuries becomes not just possible, but likely. The Cold War base, built to hide missiles and Project Power, accidentally became a time capsule preserving evidence of an ice-free Greenland that the scientists of that era hadn't imagined. It's a reminder that sometimes the most significant discoveries come from unexpected places, that military projects and scientific research can intersect in surprising ways, and that the ice, even as it's forced to surrender human engineering projects, keeps its deepest secrets until the very last moment. Camp Century's tunnels have long since collapsed, buried and erased by the flowing ice. But the samples it left behind continue to speak, bearing witness to an epoch when Greenland was green, warm, and alive, and to the possibility that such an epoch might come again, sooner than we're prepared to accept. Beneath Greenland's ice and permafrost lies a paradox: frozen fire. Methane hydrate, commonly called fire ice, exists in vast quantities in the Arctic, trapped in a crystalline lattice of water molecules that cage the methane gas under specific conditions of pressure and cold. It looks like ordinary ice, but with a ghostly white, or pale blue color. And if you bring it to the surface and touch it with a flame, it ignites, burning with an eerie, smokeless fire while the ice melts around the flame. The formations occur where methane produced by decaying organic matter deep underground or released from geological sources meets cold conditions and sufficient pressure. The resulting hydrate is stable only within a narrow range of environmental conditions. Too warm or too little pressure, and it decomposes, releasing the trapped gas. Scientists estimate that Arctic permafrost and offshore sediments contain hundreds of billions of tons of carbon locked away in methane hydrate. To put that in perspective, if even a small percentage of this methane were released into the atmosphere, it would dwarf current human carbon emissions. Methane is a greenhouse gas roughly 25 times more potent than carbon dioxide over a century-long time frame, and much more potent over shorter periods. This is where the fire ice becomes genuinely troubling for contemporary climate concerns. As Arctic regions warm and permafrost thaws, conditions that have kept methane hydrate stable for millennia are changing. Deposits are beginning to destabilize, releasing gas into the atmosphere and ocean. Researchers monitoring Arctic methane levels have detected plumes of gas emerging from the seafloor, bubbling up through warming water. In some areas, the concentrations are high enough to be detectable from aircraft. On land, thermokarst lakes formed when permafrost melts and the ground collapses are releasing methane that was locked away for thousands of years. The feedback loop is the nightmare scenario. Warming causes methane release, which causes more warming, which causes more release. Some scientists worry about a potential methane bomb, a rapid, massive discharge that could spike global temperatures catastrophically. The geological record offers both comfort and concern. Past warm periods, including the Eemian interglacial, involved Arctic temperatures higher than today, yet didn't trigger runaway methane release. The Earth system has regulatory mechanisms. Methane breaks down in the atmosphere. Ocean currents can absorb and distribute heat. Vegetation growth can capture carbon. But the current rate of warming is unprecedented in geological terms. Natural transitions take millennia. We're creating similar changes in decades. It's unclear whether Earth's regulatory systems can respond quickly enough. For Greenland specifically, the methane hydrate deposits are another hidden element in the frozen. Archive testimony to ancient organic productivity, to geological processes that concentrate carbon over millions of years, to the delicate balance of chemistry and temperature that keeps dangerous compounds safely locked away. As the ice melts and permafrost thaws, the fire ice begins its transformation from solid to gas. Whether this happens slowly enough for Earth's systems to absorb and adapt, or rapidly enough to create dangerous feedback loops, remains one of the most critical uncertainties in climate science. The ice that burns is a reminder that Greenland's frozen surfaces conceal more than ancient landscapes and fossils. They conceal massive stores of chemical energy, locked away by cold, waiting for warmth to set them free. And unlike the biological archives or geological mysteries, this particular secret has immediate, tangible consequences for the planet's future climate. Fire and ice, opposites in poetry, turn out to be intimately connected in the Arctic's chemistry. As Greenland's ice retreats, we're learning that what lies beneath isn't just inert rock and dirt, but a complex chemical system that has been dormant, patient, and is now beginning to wake. Greenland's story has always been written by forces beyond the ice. For all the focus on glaciers and climate, on what's hidden beneath the frozen surface, there's another dimension to the mystery, one written not in rock or ice, but in the sky itself. The cycles that govern Greenland's transformation between green and white are ultimately astronomical, driven by subtle variations in Earth's relationship with the sun. The Milankovitch cycles, named after Milutin Milankovic, who calculated them with remarkable precision in the 1920s, using only pencil and paper-described 3 orbital variations that influence climate over vast timescales. First, eccentricity. Earth's orbit around the Sun slowly changes from nearly circular to slightly more elliptical and back again over a period of about 100,000 years. When the orbit is more elliptical, seasons are more extreme, hotter summers, colder winters, though the effect is subtle. Second, obliquity. The tilt of Earth's axis varies between 22.1 and 24.5 degrees over a 41,000-year cycle. More tilt means more extreme seasons. Less tilt means milder seasons. Currently, we're at about 23.5 degrees, in the middle of the range. Third, precession. Earth's axis wobbles like a spinning top, completing a full wobble roughly every 26,000 years. This determines which hemisphere gets more sunlight during its summer, and when in Earth's orbit the summer occurs. These three cycles combine to create complex patterns of solar energy distribution across the planet. When they align in particular ways, less tilt, Earth farthest from Sun during northern summer, orbit more circular Arctic regions receive reduced summer sunlight. Snow accumulates year after year, and ice ages begin. For Greenland, positioned between 60 and 83 degrees north latitude, these astronomical variations are the fundamental metronome of its existence. The island doesn't choose to freeze or thaw based on local conditions. It responds to the sun's changing geometry, to alterations in the light that falls across its surface. But there are other cosmic influences, more speculative and harder to measure. Solar output itself varies. The sun goes through cycles of more and less activity, not just the familiar 11-year sunspot cycle, but longer variations that might span centuries. During the medieval warm period, some evidence suggests solar output was slightly elevated. During the Little Ice Age, the sun appears to have been quieter, producing fewer sunspots and slightly less energy. Could these solar variations have been enough to tip Greenland between habitable and frozen? Probably not by themselves, but combined with other factors, ocean current changes, volcanic eruptions affecting atmospheric clarity, methane release from warming tundra, they might have pushed the climate across critical thresholds. And then there are the true catastrophes, asteroid impacts and supervolcanic eruptions. The Hiawatha crater in northwest Greenland, if it dates to the Younger Dryas period, as some suspect, would represent a cosmic intervention in climate, history and impact that might have triggered the sudden cold snap that interrupted the last ice age ascending. Such events are rare but not impossible, and they can reset climate systems in ways that ripple through centuries. Standing on Greenland's ice, looking up at the Arctic sky, one is seeing the same stars that witnessed every epoch of the island's transformation. The same sun that melted the ice 120,000 years ago still rises and sets today. The same moon that pulled tides across shores, now drowned by rising seas, continues its orbit. The astronomy is patient and indifferent. It will continue cycling Earth through ice ages and warm periods, long after human civilization is either transformed or extinct. Greenland will freeze and thaw according to celestial rhythms, responding to angles of sunlight and orbital geometries with geophysical precision. What makes our current era different is the overlay of human influence. We're adding a new factor to the ancient equation atmospheric chemistry, altered by industrial activity, a greenhouse effect enhanced beyond natural levels. The astronomical cycles continue their slow dance, but we've introduced a new rhythm, faster and more aggressive, and it's unclear how the old patterns and the new will harmonize. The sky above Greenland is both timekeeper and witness. It has watched the ice advance and retreat for millions of years. It has seen coastlines drown and emerge, forests grow and die, species migrate and evolve. And now it watches as one particular species attempts to understand the cycles that govern this frozen world, even as that species inadvertently accelerates the latest cycle's transition from ice to water, from white silence to green possibility. The cosmic forces don't care about our narratives or timelines, but they are, ultimately, the authors of Greenland's story and ours. This is where hypothesis becomes speculation, where science touches mythology, where the absence of evidence becomes, paradoxically, suggestive. Could there have been during one of Greenland's warm periods, perhaps during the Eemian, interglacial 120,000 years ago, or during earlier warm epochs, a human or precursor human presence sophisticated enough to leave traces, yet existing long enough ago that those traces are now buried beneath ice or eroded beyond recognition? The mainstream archaeological consensus is unequivocal. No. Human technological civilization is recent, dating back perhaps 10,000 years at most. The earliest complex societies, Mesopotamia, Egypt, the Indus Valley, arose after the end of the last ice age. Before that, humans existed as hunter-gatherers in small bands, sophisticated in survival skills, but not in the kinds of material culture that would leave lasting archaeological signatures. And yet, certain pieces don't quite fit comfortably into this narrative. Homo sapiens has existed for roughly 300,000 years. For the vast majority of that span, 290,000 years, we lived as mobile hunters and gatherers, leaving little trace beyond stone tools and occasional hearths. But anatomically, modern humans are identically equipped to us. Same brains, same hands, same capacity for language and abstract thought. If they were physically and mentally our equals, why did it take so long for civilization to emerge? The standard answer involves cultural accumulation, knowledge building on knowledge, populations reaching critical densities, the development of agriculture providing surplus that enabled specialization. All valid factors. But there's an alternative possibility, one that archaeological evidence cannot easily address. Perhaps there were earlier experiments in complexity, small-scale civilizations, or sophisticated cultures that arose during favorable periods and then disappeared when climate shifted, their traces erased by advancing glaciers, rising seas, or simply the passage of time. Greenland is a particularly intriguing candidate for this speculation. During the Eemian, it was partially ice-free for 15,000 years longer than all of recorded history. If Homo sapiens, or even earlier human species, reached those shores during that epoch, if they established settlements, developed technologies, left marks on the landscape, all of it would now be either deep underwater, sea levels were higher then, and even higher when ice reformed, or buried beneath the returned glaciers. The same glaciers that preserve climate data so perfectly are also perfect erasers of surface artifacts. Anything left on or near the surface would be ground to powder within centuries of ice coverage. Only the deepest, most protected sites might retain any recognizable structures, and even those would be profoundly difficult to distinguish from natural geological formations. This is the challenge. Proving a negative is impossible, but proving a presence that was subsequently erased is nearly as difficult. Without excavation, without direct evidence, we are left with tantalizing maybes and the acknowledgement that vast stretches of potentially habitable time and space have left no archaeological record. Some point to the advanced astronomical knowledge encoded in ancient structures, the precise solar alignments of Stonehenge or Newgrange, for instance, and wonder if such knowledge might have been inherited from earlier, lost cultures. Others note the flood myths that appear in nearly every ancient civilization and wonder if they preserve memory of the catastrophic sea level rise that followed the last ice age. But these are threads without a tapestry, hints without confirmation. Mainstream archaeology remains, rightly, skeptical of claims unsupported by physical evidence. What we can say with certainty is that Greenland has been habitable, at least in parts, during multiple periods within the span of human existence as a species. We can also say that archaeological preservation in glaciated regions is profoundly poor, and that any evidence of human presence would be extraordinarily difficult to find unless one knew exactly where to look. As the ice melts and previously hidden landscapes emerge, there's a vanishingly small but non-zero possibility that something unexpected might surface. A site, an artifact. evidence of presence that predates the known timeline. Most likely, what will emerge is simply land rock, soil, ancient riverbeds, and the fossils of plants and animals. Nature's story rather than humanity's. But in the absence of certainty, speculation finds room to breathe. And there is something deeply human about looking at a map of ice-covered landscapes and wondering, could someone have been here before? Could they have looked at these same mountains, fished these same rivers, watched the northern lights dance above these valleys before the cold came back and covered everything? The ice is retreating. Old lands are emerging into light. And while the smart money says they'll reveal only geological and biological histories, there's a whisper faint, unlikely, but impossible to silence entirely. That perhaps, just perhaps, they might tell stories we never expected to hear. We are witnesses to a transformation that last occurred over 100,000 years ago. Greenland's ice sheet is losing approximately 280 billion tons of ice per year, a number so vast it is difficult to contextualize. Picture a block of ice the size of a mountain disappearing annually, multiplied by hundreds of mountains, and you're beginning to approximate the scale. The melt is not uniform. Some glaciers are retreating rapidly, pulling back kilometers in a matter of decades. Others remain relatively stable, but the overall trend is unmistakable and accelerating. Regions of the ice sheet that were frozen year-round now experience significant summer melting. Meltwater streams that were small trickles are becoming rivers. Lakes form on the ice surface, their dark water absorbing solar energy and accelerating the melting beneath them. What took millennia during previous natural warming cycles is happening in decades now, compressed by atmospheric chemistry, altered by human activity. We are running the experiment at fast-forward speed, and the results are playing out on Greenland's ice in real time. But what's emerging from beneath that ice is more than just rock and water. It's memory. Along the southwestern coast, areas that were ice-covered within living memory are now exposing soil and vegetation. In some cases, the newly revealed landscape shows signs of the Norse settlement structures that were abandoned 600 years ago and subsequently covered by advancing ice, now re-emerging into sunlight as the ice retreats past its medieval extent. Deeper inland, where the ice has been present far longer, the emerging land is genuinely ancient surfaces that haven't been exposed for tens of thousands of years. Scientists are finding preserved vegetation, identifiable to species level, that grew during the last interglacial period. The plants are freeze-dried, their cellular structure intact, as if they died yesterday rather than 120,000 years ago. These botanical discoveries are confirming what ice core data had suggested, that Greenland's recent past included multiple periods warmer than today, periods when southern Greenland at least was substantially ice-free. The land is providing direct testimony to epochs the ice had hidden. There's a peculiar temporal dissonance in witnessing this process. The landscapes emerging are ancient, but their emergence is contemporary. The melt is both a return to a previous state Greenland, becoming green again, and something unprecedented, because the rate of change is faster than any natural cycle would produce. For the people living on Greenland's coasts, the transformation is visceral and immediate. Hunting routes that were reliable for generations are changing as sea ice patterns shift. Infrastructure built on permafrost is destabilizing as the ground thaws. Coastal villages are planning relocations as storms intensify and erosion accelerates. For scientists, the melt is an unprecedented opportunity and a race against time. Landscapes hidden for millennia are being exposed, offering windows into past climates and ecosystems. But the organic material being revealed is also vulnerable exposed to air and bacteria. It begins to decompose. What the ice preserved perfectly begins to decay the moment it's exposed. Researchers are scrambling to document, sample, and study these emergent archives before they're lost forever. And for the planet, Greenland's melt is an alarm bell. The ice sheet contains enough water to raise global sea levels by approximately 7.4 meters over 24 feet. Its complete disappearance would redraw coastlines worldwide, drowning major cities, displacing hundreds of millions of people, erasing entire nations. We are not yet at the point of no return. The complete melting of Greenland's ice would take centuries, even under worst-case scenarios. But we're approaching tipping points, thresholds beyond which the melt becomes self-sustaining regardless of human actions. Darker bare ground absorbs more solar energy than reflective ice, creating feedback loops. The loss of ice changes atmospheric circulation patterns, potentially affecting weather systems far beyond the Arctic. The return of the melt is a return to a state Greenland has experienced before, but for human civilization. Built during a climatically stable period, it represents a fundamental challenge. We've constructed our cities, our infrastructure, our agricultural systems, on the assumption that coastlines and climate zones will remain roughly stable. Greenland's ice is proving that assumption false. As the ancient landscapes emerge, they're not just revealing the past. They're showing us our possible future, a world where the maps must be redrawn, where the familiar boundaries between land and sea shift, where the frozen archives of climate history thaw and speak their warnings to those willing to listen. The ice is returning to the sea, returning to the state it held before the last ice age trapped it in solid form. And we are watching, recording, measuring witnesses to a planetary transformation that our species has never experienced before, but which the ice itself remembers perfectly. The ocean has a long memory, written in salt and sediment. As Greenland's ice melts, the water flows through ancient riverbeds, pools and glacial lakes, and eventually finds its way to the sea. Each drop carries with it dissolved minerals, suspended sediments, and the genetic traces of organisms that lived and died millennia ago. The ocean receives this influx, incorporating it into currents that will carry these fragments around the globe. But the ocean is not passive. As meltwater enters, it changes salinity, affects temperature gradients, and alters the great conveyor belts of circulation that distribute heat across the planet. The North Atlantic is particularly sensitive here. Cold, dense water normally sinks, driving a circulation pattern that keeps Western Europe far warmer than its latitude would otherwise allow. Excessive freshwater input from melting ice can disrupt this sinking, potentially weakening or stalling the entire current system. This has happened before. During the last ice age's end, massive ice sheets covering North America collapsed, releasing enormous quantities of fresh water into the North Atlantic in events called meltwater pulses. These pulses correlate with abrupt climate shifts, the younger, driest cold snap being one of the most dramatic. A warming trend was suddenly interrupted, temperatures plummeted within decades, and for over 1,000 years, the Northern Hemisphere experienced conditions closer to full glacial than interglacial. The mechanism is thought to involve the ocean's circulation. Freshwater influx disrupted the sinking of dense water, slowing the heat transport northward, allowing ice to advance again despite rising global temperatures. It was a temporary setback. Eventually the circulation recovered and warming resumed, but it demonstrates how sensitive Earth as climate system is to changes in ice sheet behavior. Today, scientists are monitoring the Atlantic circulation carefully. Some measurements suggest it's weakening, though the data is still debated. If Greenland's melt accelerates significantly, the potential for disrupting ocean circulation becomes more than theoretical. But there's another dimension to the sea's memory. It records what the land forgets. Sediment cores from the ocean floor around Greenland contain layers of debris sand, gravel, organic material deposited by icebergs as they drifted and melted. These layers are dated and analyzed, creating timelines of ice sheet behavior stretching back millions of years. They show periods when iceberg activity was intense, ice sheet actively calving, and periods when it ceased, ice sheet either absent or entirely stable. The most striking discovery is how variable the pattern is. Greenland's ice is not a permanent fixture, but a dynamic feature, responsive to relatively small changes in temperature. During warm periods, it retreats dramatically or disappears. During cold periods, it advances. And the ocean remembers the consequences. Coral reefs that grew during past interglacials, when sea levels were higher due to melted ice, are now fossil platforms meters above current sea level. Beach ridges from ancient coastlines mark where the ocean once reached. Drowned river valleys show where streams flowed when the sea was lower during ice ages. The pattern is one of rise and fall, advance and retreat, drowning and exposure. The ocean has written this history in layers, patient and precise, creating an archive that complements what the ice itself records. For coastal human populations today, this history is not academic. Sea level rise driven by melting ice is already measurable several millimeters per year globally, with local variations. Island nations are planning evacuations. Cities are building seawalls. Engineers are designing infrastructure for a wetter future. But the ocean's memory suggests this is just the beginning. During the Eemian interglacial, when temperatures were only slightly warmer than today, sea levels rose 6 to 9 meters higher than present. Most of that water came from melting ice in Greenland and Antarctica. The process took thousands of years, a pace that, while catastrophic for coastal ecosystems, at least allowed species to migrate and adapt. Today's warming is happening far faster. The ocean is beginning to write a new chapter in its long memory, one where human activity plays a central role. The meltwater entering from Greenland carries not just minerals and ancient pollen, but also a warning that the boundaries we think of as permanent coastlines, ice extents, climate zones, are actually fluid, responsive, and historically variable. The sea remembers the last time Greenland was green. It remembers the coastlines that drowned, the circulation patterns that shifted, the ecosystems that transformed. And now, as the ice melts again, the ocean is experiencing a familiar pattern, one it has recorded before, but which human civilization has never witnessed. In ports around the world, tide gauges record the rising water with millimetric precision. In laboratories, scientists analyze sediment cores and ice samples, reading the archives of past climate. And in coastal communities, people watch the sea edge closer, year by year, as Greenland's ice returns to liquid form and the ocean's memory merges with our immediate reality. The sea rises. It always has. The difference is that now we're watching, measuring, and understanding witnesses to a process that has played out in geological time, but which we've compressed into human time. A transformation that should take millennia, unfolding in mere centuries. The ocean remembers. The question is whether we'll remember this moment when we could see clearly what was happening, when the data was undeniable, when the ice itself was showing us our future and what we chose to do about it. The camera drifts once more across the frozen expanse, just as it did in the opening moments, but everything has changed. We understand now that the white silence is not empty, but full of history, memory, warning, and possibility. Each crevasse is a page, each layer a chapter, each melting stream a sentence being written in real time. Greenland is not a frozen wasteland, but a library, an archive, a testament to planetary forces and temporal scales that dwarf human civilization. The secret beneath the ice is not a single revelation, but a multitude. It's the knowledge that Earth's climate has never been stable, that the boundaries we think of as permanent are temporary, that ice and warmth cycle in rhythms driven by the stars. It's the understanding that previous epochs existed warmer, greener, alive with possibilities we can only glimpse in pollen grains and genetic fragments. It's the humbling realization that humans have existed for hundreds of thousands of years. Yet our material civilization is a flash in geological time. That entire cultures could have risen and fallen during warm periods, their traces erased when the ice returned. That we are not necessarily the first to witness these transitions. though we may be the first to measure and record them with such precision. But perhaps the ice's deepest secret is simpler and more troubling. It's that we keep forgetting. The Norse settlers arrived during a warm period, thrived for centuries, and then vanished when the cold returned. Their descendants, safe in Iceland, eventually forgot the details of the Greenland settlements, forgot the extent of the warming, forgot the lessons about climate's variability. Indigenous peoples preserved warnings in oral tradition stories of advancing ice, changing conditions, lands swallowed by cold, but these were often dismissed by later cultures as myth rather than history. Scientists extract ice cores and discover that Greenland has melted before, completely, during periods warmer than today. Yet each generation must relearn these lessons, must process the data anew, must confront the implications again. We are, in many ways, the ice's students, perpetually enrolled, but frequently forgetting our lessons, requiring the planet to teach us again and again through drought, flood, storm, and melting glacier. As the sun sets low on the Arctic horizon, barely dipping below the edge in summer, endless twilight casting long shadows across the ice, one question lingers. What will we remember from this moment? Will we remember that we witnessed the ice's retreat at a pace unprecedented in human experience? That we measured, documented, and understood what was happening? That we stood at a threshold where action might still shape outcomes? Or will this too be forgotten, buried not under ice, but under the accumulated sediments of daily concerns, economic pressures, political distractions, until some future generation uncovers records of our era and wonders why we knew so much yet acted so slowly? The ice itself will not remember us. It operates on inhuman timescales, responding to orbital mechanics and atmospheric chemistry without concern for the civilizations that rise and fall on, coastlines it alternately drowns and exposes. To the ice, we are momentary, a brief spike in temperature, a sudden increase in greenhouse gases, a transient presence that will eventually be buried in stratigraphic layers alongside pollen from extinct plants and DNA from vanished animals. But we can remember. That's perhaps what distinguishes this moment from all previous climate transitions. We have the knowledge, the tools, the capacity to record and understand what's happening. We can choose to act on that knowledge, rather than simply enduring the changes as our ancestors did. The ice's last secret may be that there is no secret-only patterns visible to anyone willing to look, repeated across deep time. The planet warms, the ice melts, seas rise, landscapes transform. Then, eventually, the cold returns. The cycle continues. But within that cycle, there are human choices. Choices about how quickly the transformation occurs. Choices about who bears the burden of adaptation. Choices about what we preserve and what we let go. As the camera pulls back, rising above the ice sheet, Greenland shrinks beneath a white island in a dark sea, glowing in the polar sun, melting at its edges, revealing what it has hidden, becoming once again what it was named, a green land. The silence is not really silence, but the sound of water dripping, flowing, rushing toward the sea, carrying the past into the present, revealing secrets that have always been there, waiting for the ice to release them. And somewhere beneath that retreating ice, in landscapes just now emerging into light after 100,000 years of darkness, the land itself breathes again, ancient river valleys feeling water's touch, bedrock warming under summer sun, perhaps soon to support vegetation once more as the cycle comes full circle. The ice remembers everything. The question is whether we will.